Ladies and gentlemen, here we go. Section 7 of Chapter 10. I know, I have no idea why. It's almost, springtime coming up in the summer. I got you here in a little bit. Really warm outside, and there's a hockey stick with a hockey puck behind it. Whatever. I just like the picture. But here is, I guess, if you will, your essential question for this section, this video lesson. How do you find the measure, or really measures, of an angle, or it could say angles, of an inscribed polygon? Now we're going to talk about, I'm going to show you an example of what an inscribed polygon is. But can I tell you, you already know this word. Inscribed to you should be referring to an angle. And yes, that's the case. An inscribed angle, remember, has its vertex on the circle. So that will relate, this word inscribed will be transferred to polygons, at least the concept here, when I show you the example. So let's draw some circles in your notes. Let's do it. Here we go. So here's your circle A. You got a couple points here. You got this quadrilateral looking thing, and the question is, what's an inscribed polygon? Well, again, remember, inscribed to us in terms of an angle would be like angle C. Its vertex is on the circle. But check this out. With this quadrilateral, vertex B is on the circle. Vertex C is on the circle. Vertex D is on the circle. Did I say C? I meant E. Sorry. C, B, E, and also D. All four of those vertices are on the circle. And if that's the case, anytime a polygon has all of its vertices on the circle, that is, by definition, an inscribed polygon. Now, does it have to be a quadrilateral? Certainly not. We can do this. Let me get rid of these drawings. Let me get rid of this thing. Let me put a couple other points. So let's say, I don't know, I go from, whoops, back up. Nope. So I go from, erase this, erase that, and I'll go another point. So from D, I'll go over here to the circle. You can see it change in colors. So that vertex is on the circle, that vertex is on the circle, that vertex is right there at E. So if I grab the hold of any of these points, as long as these vertices stay on the circle, I don't care where they go, doesn't matter. That is, by definition, an inscribed polygon. More specifically, it is a 1, 2, 3, 4, 5, 6-sided shape, so it's an inscribed hexagon, technically. Could you have an inscribed dodecagon? Sure. It'd be 12 sides, 12 vertices on the circle. Could you have an inscribed pentadecagon? You betcha. Could you have an inscribed nonagon? You betcha. But we're going to talk about, in this video, a theorem that just deals with an inscribed quadrilateral and how the angles are related in that. So let's do that. Let's go to the theorem. Okay, so yeah, back to this picture. You got it, but here's the theorem, and I actually left it out intentionally. I left it blank here, so I didn't finish it. We're going to use it. Go back to the geometry sketchpad. I'm going to show you how this all works out, and you might be able to make a conjecture yourself before we get there. I hope you do, because I want you to think about this. If a quadrilateral is inscribed in a circle, then its opposite angles are blank. Well, if I have this circle and I have this quadrilateral, it can be anything. But this quadrilateral, if it's inscribed in this circle, the question is, what's the relationship between this angle and its opposite angle way over here? Are they congruent? I don't know. Are they... I have no idea what else they could be. We're going to find out with this theorem. And likewise, if I change, what's the scoop with this angle right here, this guy, compared to this angle over there? Is there a relationship among these opposite angles? Well, there is, and we're going to find out what that is to fill in this blank. So, back to sketchpad, draw another circle. So here's the same thing I had before with my definition of inscribed polygon, but I have inscribed quadrilateral with C, B, E, and D as the vertices. This is circle A, and what I want you to notice is this. I'm already highlighting for you a pair of opposite angles. And notice, no, if you were thinking they're congruent, wrong-o. So here's angle CDE, that's 74.53. And angle CBE, this guy over there, the opposite angle, that is an opposite angle in the quadrilateral. But notice, no sirree Bob. Who's Bob? I have no idea. No sirree Jimmy, no sirree Sari, no Sari, whatever. These angles aren't congruent. Now, could they be? You betcha. I could make these angles congruent, I bet. Let's see. I'm sure I can make them congruent eventually, get them close to 90 or get them close to what. I could do that, but that's not what I'm talking about. Anytime a quadrilateral is inscribed in a circle, something happens to this angle D and angle B. Do you see it yet? Do you see it? What's the comparison? They're not equal. Well, here it is. Bam. There it is. If I take angle CDE and I add it to angle CBE, these opposite angles, they add to 180 degrees. What does that tell you? That tells you that they are supplementary. Oh yeah. No wait, they don't form a straight angle. I know. There's many different ways that angles can be supplementary. So in this case, angle B, that's this one, and angle D, that's this one. Those guys are supplementary. And watch this. No matter where I take this point C, it's changing these angles tremendously. But notice the sum never changes. It's because the theorem is that these two angles are supplementary. Yep, I'll move it over here. I'll move angle E over here. Whoa, weird. Weird angles, I got you. But if you look at angle D, really, really small, 23-ish, and angle B, really, really big, 156, almost 157. If you add them together, they're supplementary. Now, what if I do this? Let me keep that up there, and let me show you the other pair of opposite angles. There they are. So now I'm looking at angle DCB, that's this one, and angle BED, that's this one right here. So that's a pair of opposite angles. These guys, those guys right there, across from each other. Wonder if they're supplementary. Well, if you look at it, and you look at 99.7 and 80.2-ish, you betcha, they would also be supplementary. Notice, bam, those angles add to 180 degrees. So it doesn't matter what this bad boy looks like. The opposite angles are always supplementary. Always. I don't care where it is, but the key thing, boy, I hope you circle this, I hope you underline, I hope you start. It is only in an inscribed quadrilateral. Awesome. So let me go back to the PowerPoint so you can fill in the actual blank, and we're done. And I'm excited to practice this and master this simple little theorem, but very useful theorem in class. So I'm back to this theorem, and here it is. If a quadrilateral is inscribed in a circle, again, only quadrilateral, not pentagon, not hexagon, nothing, just a quadrilateral, then its opposite angles are supplementary. Awesome. Write it down. Let's use it. And by the way, if you have to use this in a two-column proof, that's right. You don't write Theorem 93. You don't write supplementary. You don't write quadrilateral supplementary. You write if a quad is inscribed in a circle, then its opposite angles are supplementary. There you go. Rock and roll. We'll see you guys later. Peace.